Today, we're simulating what would happen if a black hole came for Earth. But that's not all. We're also going to simulate black hole collisions with Jupiter, our sun, even the entire solar system. Let's get into it. Hey everyone, welcome to another episode of Space Sim. It's What If Space Sim.
That is correct.
Today, I'm here along with Stu. Again,
hello.
I'm Peter. And this is a project of What If, and we're going to take you through the Space Sim program where we simulate things in outer space. First of all, let's talk about black holes.
Yeah.
Black holes are not what people think. They're not this big vacuum cleaner that goes all through the universe and just starts sucking
everything
things
up.
up.
Yeah.
They're just an enormous amount of gravity all in one space.
Yeah. So it feels like it's sucking everything up because the gravity's so huge that it is pulling everything in, but it's not really that vacuum cleaner.
It's pulling on planets, it's making them crumble into little bits, and those little bits are going and becoming part of the black hole.
Yeah.
But it's not a hole.
No.
No, it's an object of mass.
Exactly. So.
It's an object of enormous mass, often billions of times as big as the sun.
First, we're going to start with Earth. So the way that we've set it up, we've had our wonderful What If production team help us out with this. So the Earth is pretty dang close to this black hole.
Okay.
Excuse my language.
So in terms of
it's about
astronomical units.
1, 2, 3, 4, about 5 Earths away.
Okay, 5 Earths away. An astronomical unit, though, is the distance from Earth to the sun, and you'll be hearing a lot of that, I think, today.
Oh yeah, we're gonna talk about AU nonstop.
AU, it's a short form.
AU. So yeah, it's about 5, 6 Earths away. That's closer than the moon is to Earth currently. So this black hole is close. So what you're gonna notice during the simulation.
Sorry to stop you there, but I would think that if a black hole is an enormous amount of mass, it's exerting gravity upon the Earth.
Yeah.
And so to be that close, closer than the moon, which also exerts gravitational pull,
thus
or
the
tides upon the Earth,
yeah,
this thing would already be pulling Earth apart, would it not?
Yeah, so that's the fun part. So if we look down here, this is a timeline. Now, if you remember the last time we did it, when we were colliding planets together and stuff, we had a timeline of like seconds, minutes, hours of how long it would take for these things to collide and create things. What you're noticing here is we're already down to 10th, 100th, 1,000th of a second.
Right, but 0 hundredths of a second, is it? Or we just haven't started it?
Right now we're at 0, but you can tell that since we're already putting it into the 1,000th of a second, this is gonna go really quick. Okay. So quick that if I press play,
I won't see it.
You won't see it. Are you ready? We'll break it down, but you'll see how fast everything. If a black hole were to appear right at this very second, here's how fast the Earth would get sucked in.
Okay.
There you go.
It's already happened.
That's done. So, what you're gonna notice right away, so I'm gonna take you step by step here, because that's how quick it is. If we were to slowly move it aside, this is slow. We are now 0.05 seconds into this black hole appearing, and right away, you're noticing an increased amount of temperature. You're noticing the Earth is starting to, one side, you're getting that tidal force, which is super cool, and the Earth is already starting to just get pulled in by the black hole's
now the
gravity.
This says the temperatures are going up. Obviously, is that because the core and the magma are being pulled toward the surface of Earth?
Yeah, also with gravity, when you're having that much pull, everything, including atoms, everything is getting pulled that quickly. And because it's getting pulled that quickly, it creates heat, creates energy. And what you're gonna notice is that as we speed this up, Earth is gonna go from this once beautiful planet that we love to an orb, just a little white orb. And that's because just within the matter of barely 0.2 of a second, the Earth has completely been destroyed by volcanoes, eruptions, just atoms themselves.
Yeah, I would imagine that the heat would also be evaporating the oceans.
Yep.
And so that could be a lot of condensation. I'm sure that's even wiped out too. There's
all these gases. And then so basically, black hole appears within 0.2 of a second, done.
And Earth is just a puff of smoke.
Yeah, exactly. And so what you're noticing here, this is where the fun part comes in, is that Earth is starting to get pulled pulled in because
Wow,
it's
like the
too
middle,
far
right?
away.
Yeah.
We're already past something cool called the event horizon.
The event horizon. You can't see the event horizon. Well, why doesn't the Earth just, hightail it the other way and try and get out of the event horizon so that we're not affected at all?
Well, unfortunately, nothing can escape the event horizon.
Nothing can escape the event
That's
horizon.
what makes it so cool. That's what it has such a cool name. Once anything has passed a black hole's event horizon, which is
Yeah.
basically how close you have to be to a black hole for like a huge amount of its gravity pulling you, nothing can escape, not even light, which is super cool.
Which is why a black hole is black.
Exactly.
Because it's got all this stuff in it, including it's sucked in all this light, but the light can't escape the event horizon.
Exactly.
So it's not shining back at us and we can't see it.
What's actually really cool is that, like, say the Earth was here and just to appear, and someone else was to look through a telescope to look at us
Yeah.
in real life and not through a simulation, this would appear frozen because you have to look through a telescope, you're waiting for light to hit your eyes. There's no light there, so it would just kind of be frozen and then it would just disappear. Just everything gone. So
Scary.
yeah. And so what we're seeing here is that
And now you see it's so take us back there where it goes to egg shape.
yeah.
So what's happening is the gravity or the tidal force of the black hole is pulling on the Earth so much that it starts to stretch it, and Earth goes from being a sphere into being an egg shape, oval with an egg shape.
Yeah.
And then it just starts, it's obviously past the event horizon here.
Yeah.
And is this the beginning of what we call spaghettification?
That is very true. I mean, this spaghettification is hitting pretty early here. If it was farther away, maybe that process would be a little bit more drawn out, but it's starting immediately, and what we're doing is we're seeing that the spin around here.
Now, if you think spaghettification sounds a little bit like spaghetti, you're correct. That's what it was named after. So the idea is that the black hole is pulling so much on every single particle on Earth, every single atom, that they start flowing into the orbit of the black hole. See, this is what's called an accretion disk here, going around and around the black hole. And the spaghettification is that each of the molecules goes into like almost like single file, and we turn from an enormous Earth into just this like long stream of spaghetti noodle that's being sucked toward the black hole.
It's really cool. It's almost beautiful in a way.
It's fun how science sometimes comes up with fun things, like names like spaghettification.
It is I'm sure they could have come up with some sort of Latin word for worm or something, but I like spaghettification.
Yeah, it's way more fun.
Makes it much more fun. So yeah, I thought we could go through.
Do you think Galileo came up with that? He was Italian.
Was there spaghetti back in his time?
Well, there was pasta. I think everything was spaghetti, wasn't it?
Not everything.
Everything was
You have, like,
macaroni. Everything was macaroni.
so they called it macaronification back
Yeah,
then. Yeah, but then it's
probably.
changed over time because we've evolved to
Right.
have spaghetti and stuff.
Okay, let's take another look at this, but I see you've moved the Earth a little further away from the black hole
Much
at this point.
farther away. Right now we're over 50 Earths away.
This is fantastic. So now
60 Earths, my apologies.
So sorry, what is this? This little grid that you've got signifies.
Just kind of shows how far everything is. So, if we have the black hole here at 0, then it's about, you could fit 50 Earths here between the black hole and where Earth is now.
Okay.
I'm not putting any velocity on it, nothing like that. So we're just letting the gravity of the black hole kind of just take over here. And as we hit play, we can kind of get like a stretched out version of what happened.
So we're already moving forward, even though you said there's no velocity for Earth. So
This is all
fishing. This is a
Pulling.
fishing trip by the black hole.
And it's
and Earth's
certainly
already burning up. So hold it, stop it right there.
This would be the far approach. This is us really, really far.
Oh, from far away. Okay.
Yeah. Yeah, this would be the far approach, I'd say. We're this is when
Okay.
we start to feel it.
So this is more than 60 Earths away.
This is about 50 Earths away.
Okay, 50 Earths away.
50 Earths away, and this is our Earth-sized black hole. In reality, like some of these black holes, just to give you a size.
Okay.
Let's take Sagittarius A, which is in the middle of our Milky Way.
Sagittarius A is a supermassive black hole.
Yeah, so you start to realize this is how big it is. So if I were to delete this, You ready? And this is me zooming in. You can really
Okay.
see just how there's Earth. See, that's all of us right there.
Okay.
I put Sagittarius here.
It's the size of.
About 20 times the sun. See, now our grid has changed to the radius of the sun instead of how big the Earth is. See, and then if we delete it, look how we have to zoom in. We have a black hole much more size appropriate. This one's closer to the size.
Primordial black hole.
Yes, this one's a lot more closer to the size of an Earth.
Right.
Yeah, right now we're about 50 Earths away. It's a lot farther, and now we can kind of see more of a breakdown of kind of what's happening to Earth as we start this simulation.
Right. Okay. And we are how far away at this point?
50 Earths,
50 Earths,
and we're slowly building up speed.
What is our time? How far away? Can we tell how many minutes or hours or seconds away from the black hole we
Well,
are?
right now it's been about 5 seconds, and we're already speeding at least 1 to 2 Earths per second.
Okay. And then you can see here, that's where the Earth starts to.
Boom.
That's where Earth starts to start on fire, and you can see it's already being pulled a little bit, losing its spherical shape, getting squeezed into that egg shape, like Mork when he came from Ork. If anyone remembers the 1980s show Mork and Mindy.
Is that what is
Yeah.
Mork an alien show?
Mork was an alien from the planet Ork, and he traveled in an egg, similar to what we're seeing now, except, whoa, that's the end of the Earth.
That's like kind of event horizon. You can kind of see that just
Right, so it's crossing the event horizon. We're not seeing the light anymore because it's being sucked in by the black hole.
Yep.
And it doesn't even become part of the accretion disk. We're not seeing the accretion disk.
No. So this is a simulation, so obviously not everything's perfect.
Okay, so there's no accretion disk here, and that's because this is space sims. It's not actual space. We're not looking at actual pictures of space. The Earth did not just get sucked into a primordial black hole. But if we were looking at an object in space being devoured by a primordial black hole, there would be an accretion disk around it.
Yes, that is correct.
We can maybe be able to show you that later. I know we've got some simulations that.
Oh yeah, we definitely
that.
will. So let's kind of talk about what people are kind of feeling in these first kind of moments. So a black hole appears. Now this isn't like last time where it was 0.2 of a second and we're all wiped out. We're 0.2 in a second and we're still here. We're still kicking.
Okay.
But it doesn't take long for this stuff to kind of kick in.
Right. So what would be happening right now would be like we'd be seeing tsunami. This would just be on one side of Earth. At
That's
this point,
correct.
right?
So this is, I believe that's Africa.
That is Africa.
They would be feeling a lot more
In
of
fact,
that
there, look at that.
gravitational
There's
pull.
the Strait of Hormuz, right there. You can see
Nothing,
it, yeah.
nothing would matter at this point.
Yeah.
Just everything, even that oil getting sucked out.
So presumably on this side of Earth, there'd be some effects on the other side of Earth, but on
Yeah.
this side of Earth specifically, there would be, tsunamis.
Yep.
Be changes in tectonic plates. We'd be feeling earthquakes.
Yep.
Probably a lot of people would have perished by this, even just at this point. Looks like Earth is still intact, but actually there's a lot of stuff going on there.
Oh, yeah.
Volcanoes would be
Exploding.
erupting wherever volcanoes can erupt.
Yep.
Likely, would the water be starting to be pulled off of Earth? Would objects be starting to lift off the ground?
This would probably be around this area because as you notice, it's starting to, that shape of Earth is really starting to change. You can kind of see like, okay, there it is, our beautiful sphere, and then you can kind of see it's kind of getting squished a bit. So it would be about here where, yes, things would start to come off. What we talk about for
Okay.
tsunamis, it's like if water isn't pulled off the planet, at the very least, it's pulled off enough to then Earth's own gravity to create this mixture of typhoons
Yeah.
and tsunamis and
And likely, would
Terror.
humans be lifted off the ground?
You'd definitely feel it. This is the point where you would really start to feel it. Whether or not we'd actually be pulled off, I think most, if not all of humanity would be dead before anyone would really start to
Even
be
at this
lifted
point
off.
where it seemingly looks like we're still kind of Earth. It's not a pretty sight.
Yeah.
down there. So what's happening here is it's a fight between gravities, and the black hole has so much more gravity than Earth, so it's pulling things off away from the core.
Yeah, and that's what we're seeing here. Look at these explosions. Beautiful in a space sim, terrifying in real life. And you
Yeah.
kind of see that black hole in the distance there as...
I can't see it because it's a black hole.
you can kind of see there's a little bit of
Oh
warp
yeah,
in.
there
You
we
see
go. That's a
that?
little bit of accretion disk.
Yeah, a little warp kind of going on with all the stars. It's a nice fun effect. But this is, look at that. Earth is absolutely pure egg shape right now.
Wow.
Core getting pulled out here. Earth is just trying to stay alive as a planet.
Yeah.
Everyone's gone.
Everyone's dead at this point. Okay.
Yes. And then...
So this is where we begin, and we're still, I don't know if you can tell how many AUs away or how many
At this
Earths
point, we're
away
about 25.
So we've
25
gone half,
to 30.
gone about halfway from what we were before.
Yeah.
And at this point, the entire Earth, every sort of
Living
molecule
thing.
is breaking up.
Yeah.
Not molecules, but anything that, any building you're in, bits of me are probably
all over the place. We're all just kind of melded together. It's a beautifully horrific sight as we finally get sucked in. Black hole gets its spaghetti.
That's the spaghettification.
And that's it.
The debris flow into the accretion disk.
What if we try to race it, Peter?
Okay, so now we are going to see if we can run away from the black hole. Run away, run away.
Yes, you can see from the trajectory what it might happen, but we're gonna let it play out.
What's your trajectory here? Looks like we're in some sort of orbit here. We're going in a circle.
So currently we are around 20 Earths away from where the black hole is.
That's
so a little
not
bit
many
closer.
Earths away.
It's not many Earths away, but I think we really want to emphasize what's going on here. So currently we are going over 10,000, no, more than that. We're hitting almost 50, if not 60,000 kilometers per second.
Per second?
Yeah, that's how fast Earth has to go to even kind of get away. So if we do this...
That's what's called the escape velocity.
Yes, so...
But like I say, Earth doesn't even have the escape velocity to escape the sun's gravitational pull.
So if the black hole appears, there's nothing we can do. That's just it. But if we were to somehow push ourselves to go really fast.
Okay.
So
and we would do that with
technology.
We just like somebody would on each side would just row really fast along the Pacific. And
yeah, I think if we work together,
creating,
well, that would just spin us in place.
Kind of like making waves in the bathtub.
Yeah, well, yeah,
like
I think we just do this to our doom, basically. It'd be like a bowling ball.
Okay. So, but we could maybe hook up.
Have to put like rockets on.
We need jet propulsion of some sort.
Yeah. So somehow we're able to hit jet propulsion of over 50,000 kilometers per second, which should put strain on us, but it should be able to get us away from the black hole. So let's hit start and let's see what's kind of going on.
So
here.
we got the jets right there.
Yeah.
Nice.
We're like flying through. It's pretty good, but you start to notice something.
Ooh, we start to burn up the other way.
We're still burning up because the gravitational pull of the black hole is so strong.
So it's pulling on Earth, Earth's getting away, but everything, it's like the friction of everything moving both ways, moving forward very fast and being pulled backwards.
Yeah.
So there's a lot of friction happening there.
Exactly.
That's heating up the atmosphere.
Even though we're pushing Earth really fast away, the core of Earth is still being pulled. It's not like Earth's gravity is suddenly changed or we're doing anything. We're just pushing it really fast. So right now, we're about, as you can see, we're kind of far enough away where things have slowed down. So part of Africa.
I don't know if slowing down is a word. Is it slowing down?
Slowing down, it's
slowing down. Is this similar to when a spaceship tries to leave our atmosphere? They need a heat shield.
Yes.
And a heat shield to re-enter the atmosphere.
Yeah, that's a good way to say it, because if this would be kind of like, because Earth doesn't really have a heat shield against a black hole. It's basically impossible to do.
Yeah.
So what you're kind of seeing here as we kind of continue is that, even some parts of Earth have been changed entirely. So Earth is no longer a sphere. It is still slowly turning to
shaped
spaghettification. The black hole is pretty far away. We can't even see it anymore. Yeah, it's kind of nice actually. The whole point that we're trying to make from this is, as we start this, is that, as we put Earth closer, as we try to get Earth far away, it doesn't matter how far away or how fast it can go. Earth is changed forever.
Right. Once our shape starts to change, that's the end of
Exactly,
End of
because
it. Okay.
Earth isn't able to hold its core, and so it's going to get downgraded as a planet. At this point, we're all dead anyway. So even though Earth made it out,
Right. But there
Didn't
will still
really.
be maybe bacteria on Earth, and they can still, start a new life form,
a new world.
a new world. So the
A
Earth
new-
could carry on.
It could. It could.
Everything would be evaporated, and there'd be volcanoes and tsunamis and earthquakes everywhere. But that will eventually settle down,
That's true.
and Earth will start anew in a new orbit, in a new.
Galaxy far, far away.
Or would it still be in our galaxy, or still be in our solar system almost, wouldn't it?
If it had to move away fast enough, it'd probably be on a collision course somewhere way out. So
My guess is that if the black hole has gotten this close to Earth, it's probably already gone through the sun.
the sun, the Jupiter,
Right.
all that stuff. Speaking of Jupiter,
Jupiter.
should we?
Let's
move on?
go and see what happens around Jupiter. Okay, next up in our planetary neighborhood is the largest planet in the solar system,
The largest
Jupiter.
planet in our solar system.
And are we using same black hole? Is this going to be our primordial black hole?
This one is a much similar size to Jupiter, as you can see, because
Okay.
if we kind of zoom in and compare the two sizes, you can kind of see, whoa, a lot similar of a size to Jupiter, even though it's warping it. Because comparatively, if we looked at Earth, right, and we were to look at Earth on Jupiter, it's about the size. As we know, 2 Earths can fit into that
Square?
the great red,
into the great red spot.
Yeah, so we have now increased the size of the black hole to make it more of an even fight. I don't
Okay.
want to say even.
Well, it
It's
wouldn't
not
even be even because, you can have a black hole that's the size of a nickel, and it would still be probably more powerful have more powerful tidal forces than Jupiter could withstand.
Yeah, which is terrifying thing to think about.
Black holes are scary.
Let's all right. Let's open this up and let's start the simulation and start to see kind of what's going on
Commence
here.
simulation. Let's do this.
So here we go. It's already starting. The accretion disk is going around. Look at that. It's gorgeous.
And where's our planet?
Our planet's
It's
gone.
just the end. Oh, okay, I see.
Let's remember we're pretty close.
Okay, I
Let's
see.
Let's see how
This
close we
went
are.
too fast for me to follow.
Yeah, so we're about. Keep in mind that Jupiter is bigger. So we're about the radius of the sun away.
Okay.
So you can fit.
Looked like about 6 Jupiters away, was it?
These are Earths.
Oh, those
so,
are. So
yeah.
about 6 Earths away.
No, it's closer because these are huge. So this is 30, 40 Earths is here, and this is about
I don't know what your math system is here.
60
I don't really understand
Earths.
it.
It's
Follow along with Stu.
a lot of Earths going on
Yeah.
here. It's close enough, I would say. That's a
Okay.
good way to describe it. And so when we start this
Close enough.
when we start this simulation, I think you're going to see something very similar to what we saw with Earth.
Well, I'm going to imagine that you're going to see something very similar each time anything runs into a black hole. Isn't that that's sort of the way things go? Is that
That's how
you
physics
will,
work.
Yeah, you get pulled toward it.
Yeah.
You will start to wow at the center, turn into an oval shape, and then everything you own or everything that you've ever accumulated on your planet will start breaking down into little bits and turn into spaghettification, and then start spinning around the black hole as an accretion flow.
Yeah.
Also an accretion disk.
A lot of accretion.
And
going on.
then things will get sucked in and they'll be in the blackness, so you'll never see them again.
Yeah.
What's different with Jupiter, though, is that Jupiter is a gas planet.
Yeah.
It's a gas giant, to be honest.
Gaseous
So
giant.
it is very gaseous. That was also my nickname in high school, the gaseous giant. And what will happen with Jupiter here is, what we know about Jupiter is it's layers upon layers of hydrogen and helium. So those will be the first things to be pulled off.
Yeah.
Likely pretty quickly before the rest of Jupiter, but
Yeah, that's kind of what you're seeing here on this simulation. If you remember last time, Earth kind of turned into that white sphere, like just kind of like full scorched Earth, just boom. But here, what we're seeing instead, because this is a gaseous giant, you're seeing this these explosions, this high heat start to take place almost immediately, and that's that hydrogen and helium crashing, being pulled together and stuff like that. And so it's going to start a little bit earlier, and it's going to continue to just kind of build and build, which is
so if you stop it there, you see that's the gases being pulled off to the left, and then on the right side, this is what we assume to be Jupiter's core.
Yeah.
We don't know much about Jupiter's core. It's not the same as Earth, where we have this giant iron core.
Yeah.
Scientists aren't 100% certain, I don't believe, about what it is. It could be sort of partly solid, partly liquid.
It's tough to get. You can't really get a probe in there.
Yeah,
unfortunately.
you really
so
can't.
It's maybe we'll do a what if. Maybe
we'll do a what if on it. I think we have done several what ifs on what's at the center of Jupiter.
Let's see that right now.
Yeah.
Put it on the screen.
Don't forget to like and subscribe.
But yeah, so this is what we're seeing right here is what you're talking about. There's that core and there's that hydrogen and helium crashing together. And what's really interesting is, a black hole like this wouldn't just appear with nothing there. There would probably be its own accretion disk. So it would also start to interact with other debris and such that the black hole has sucked up over.
There should be, we would, if we were there, we would see the accretion disk around it. Yeah.
And instead, what we're kind of doing is we're seeing an accretion disk kind of being made as it slowly.
Tell me about this little separation here. How they're, we go up in a little bit of a bridge over top.
Well,
and there's this line there.
Yes. So what this is kind of saying is that this line here is that intended path of of Jupiter kind of orbiting the black hole. So we were talking earlier about. I know you mentioned this kind of line here.
It's like a phantom trail.
Exactly. So if the black hole was more like a sun or another planet or something like that, this is the line that it would follow. This very nice, easy line.
That's the intended orbit.
Exactly. But keep in mind, a black hole is warping space and time and light. So what they did in the simulation is they're kind of showing it's like, okay, it could be going in a straight line, but the black hole is kind of warping the way that it looks. So it is intended to go in this kind of way, but the black hole is just kind of like look at that. That just looks cool, So that's the intended line. This is kind of what it's giving off right now.
It's giving accretion disk.
It's giving accretion disk. And what's cool here is you can see that. Do you see the gases there?
Yeah, I mean they're all gases, are they not?
Yeah, but like the gases near the tail.
Okay.
That's really cool because
that's the only gas that hasn't ignited at this point.
Yes, this is.
Or it probably could also be on fire. It's just not as dense as the.
Exact, or it could be different types of debris as well.
Could be the core.
Could be the core being torn apart and stuff like that. So this is what we're kind of seeing from Jupiter.
Okay, so let's go through the timeline of how this goes a little bit slower so that we can have a better look at it. Right now we're sitting, what is this, 3 suns away?
Three suns away, yes.
3 suns away from the primordial black hole, which you can barely see there, but it is there on your left.
Yeah.
There it is, and that's zoomed in, and that's really cool. I love when they move through
blows.
space like that. So he's bearing down on Jupiter right now.
Yeah, he's pulling Jupiter towards.
So at this point, 3 suns away, we're probably just starting to feel the effects, or we've already felt the effects a little bit already. The shape is starting to distort already into an egg shape, so that's it's starting to bulge at both sides. And the clouds are starting to, this is hydrogen and helium clouds. The colors and the lines aren't mixing, but you can bet that those gases are all being mixed together now, and this is probably one color, Jupiter at this point. It's a lot more fluid than Earth. Earth, obviously, we've got our liquids on the surface, but Jupiter is, as a gas giant, not really a surface. It's gases. Oh, look how they have a little texture there.
Let's pause that.
And then they just get sucked up.
Yeah.
Okay.
So you're talking about this is that spaghetti. It's starting to really stretch, and gases are starting to come off. Here
and I was just going to say, because it's gases rather than Earth is liquid and mostly solid, those gases are flying off the away from the planet
Yeah.
much faster than Earth was disintegrating
Yes.
or bulging.
Yeah, it's very true. And we're starting to see, look at that spaghettification just really start to kick in there. And it just getting sucked into this black hole.
Looks like a giant dirigible.
Dirigible?
Like a blimp.
Yeah, and then this is kind of where Jupiter is just going no more, right? Just absolutely getting...
Yeah, so it's actually not getting sucked directly in there. It would probably be sucked into the accretion disk first.
Yes, so this is obviously, simulations aren't perfect. So, but it is a good example to kind of show that event horizon. See how it just kind of boop disappears?
Right. So when you're seeing that light disappear, that means it's crossed the event horizon.
Yeah, and now it's going to join the mass, the center mass of the black
And it still
hole.
looks very thick, but it's actually a long stream of
Yes.
thinness in the
The
spaghettification.
farther we kind of get away, we put Jupiter away from the black hole, the more of that spaghettification will really start to show as time is. Because the more time we put between that spaghettification, the more it can really start to stretch out.
String out, yeah.
Yeah.
Okay.
And we're starting to see that right now. We just put it around an extra 2 or 3 suns away. So it's a little bit farther, and you can start to see that egg shape really starting to talk.
I love the line coming out the back. It's like the little jet propulsion.
Yeah, it's like it's got a little...
Little tadpole. A little spaceship.
It does look like a little tadpole. And look at that. You really start to see that spaghettification come in here, and then just sucked in there.
And that's the end of it.
And that's it. And that's Jupiter.
So that was seemingly pretty easy.
Yeah, it was all done in 2 minutes. 2 minutes,
Wow.
and Jupiter's gone in an instant.
Now, this isn't always the case for black holes. Sometimes they'll suck things in 2 minutes, but sometimes things might take hundreds, millions of years.
Millions of years, yeah.
Okay, so let's do what we did with Earth and see if the planet Jupiter is able to escape from our primordial BH,
Yes.
which stands, as we know, for black hole.
Yeah.
My guess is that it's got no chance that black holes exert so much mass and tidal force on planets that you're not going to be able to get away. But there is probably a mathematical equation to it. As long as, number one, as long as you haven't passed the event horizon, because once you pass the event horizon, it's game over. You'd have to go faster than the speed of light to escape.
Which is
Which
impossible.
doesn't escape.
Yeah.
It is impossible. That's why light doesn't escape.
Mm-hmm.
So your best bet is to start from far away
And try and outrun as fast as you can.
and try and run as fast as you can. So
Yeah.
as soon as you see a black hole off in the distance, turn and run.
Yeah, but I feel like at the point that you can see it, that's too late.
It's too late
you know?
because we are what here? 6 suns away, 60
We're about
suns away.
2 suns away.
2 suns away. Okay.
So it's kind of, we're pretty close to, we're pretty darn close to this black hole. But
Okay, so my guess is even at this point, 2 suns away, this black hole is probably exerting some tidal force on Jupiter already.
oh, 100%. If we were to just simulate this with 0 velocity,
Yeah.
within a matter of seconds, Jupiter is being pulled into the
I
black
can see
hole.
it bulging right there.
It's
Yeah.
bulging. It's only been 30 seconds in time
Okay.
as the spaghettification starts to happen. Nom 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 nom. Look at that beautiful.
Nice
and
spaghettification.
Nice spaghettification. And within 1 minute, gone.
Gone. Okay.
So-
So that was 1 minute in the space of 2 suns.
Yes. So
That's pretty quick.
We're gonna have to really kick up the speed to really go there.
Okay.
So
That was at 0 kilometers per second. or
that was
meters
just
per second,
Jupiter sitting there.
Yeah,
Nothing
just sitting
happening.
stable.
So let's see what happens as we increase. So this is the velocity line. And you can kind of see that as we try and get away from the black hole is still obviously pulling more. We're
Right.
at over,
There's still invisible gravitational pull. Not pressure, but it's pulling that planet in.
Yes, and so even now we're at 100 kilometers per second moving in the opposite direction.
And that's
Black
still
hole
not
is still
enough.
winning.
Is it chasing us or is it standing still?
It's just standing still. There's no velocity. It's just its gravitational pull is that much, which is crazy.
So that means Jupiter has to speed up.
And we're gonna keep speeding it up. So we're at 300, 500, 1,000 kilometers per second. This is per second. Keep increasing it. as we keep going more and more and more and more, we have now
Here we go.
seen, this is that slingshot effect. So what's going to happen here is that it has enough velocity at around 20,000 kilometers per second to slightly get away before it breaks apart and gets sucked back in. So we can kind of see that on a little bit of a speed up. See, it's starting to get away, but then you see this is when the bulging.
Uh-oh.
And that's not good. And once that bulging starts to happen, the core is gonna, become,
Core is breaking up, and that's kind of the end of the planet.
and that's the end of the planet. And so now this is where that slingshotting back. See how it's kind of staying in place, and look at that. Done.
But like we say, the black hole is not moving. It's actually Jupiter's moving. But it looks here like black hole's moving.
Yeah, it's just pulling it in. It's just, if anything, if I click the black hole, it's that's what's happening with Jupiter.
Oh,
See?
and this is like a little bit of a worm.
Yep. So yeah, now we're gonna start increasing speed to get away more, and that slingshot really starts to increase. You see that?
Okay.
And now we're hitting.
When you say slingshot, it's more like a bungee cord, right?
Bungee cord's a
You're
good
getting
way
to
to
the
describe
end,
it.
and then
Yeah.
you're like, woo, you're being jerked back.
That's a good way to describe it. Yeah.
Yeah.
Like you're running as fast as you can, and then
I guess it's kind of like slingshot. You're pulling something to this length and then letting it go.
Yeah, and then
Yeah.
it's same different thing,
Yeah.
but kind of. I like bungee cord because it feels like you're trying to run away, and then
Yeah.
you're sucked back in. So right now, C represents that we can see here is the speed of light. So currently we're at about 1/10 the speed of light, and the black hole is still going to pull that Jupiter back in. So
Wow.
we have to keep increasing it, and it's about at 11% the speed of light is when Jupiter is actually able to escape.
And that's more than 30,000 kilometers per second.
That's yes, it is going very, very,
1/10 the speed of light.
very quickly. So if we start doing this, Jupiter's off to the races, and it's doing it. Peter, it's getting away.
No, but that little line means
That's
it's going to be sucked the other way, doesn't it?
No, this is the velocity. It's kind of
Okay.
like, think of it like a trail.
So we're starting to expand, and that means
Well-
we're getting some tidal force from the black hole.
This is us running away. So keep in mind, we're escaping the black hole's gravity, but
Not for long.
well, what you're kind of noticing is that even if we escape, Jupiter's not the same, right? Something's happening with Jupiter. It's becoming, it's turning into a 6-inch delicious sub.
With what on it?
Prosciutto.
There's no lettuce because we know
salami.
there's no water.
Yeah, I see a little bread on top,
Okay. Cheese, provolone.
I see another slice of bread in the middle.
Sub sauce.
I don't know what that means. Is that
Sweet
ham
onion
and-
chicken teriyaki sauce.
That's
That's what they put on subs. Sub sauce.
what does this look like to you, Peter?
That's a Romano bean.
Romano bean?
Yeah,
I've never
actually,
even
a
heard of
Romano bean would be a little bit more pinkish in the middle. This might be more of like a dried pinto bean. You know what I'm talking about.
that. I'll be honest, Peter. I don't know my beans.
You don't?
No.
Do you ever make chili
No,
stew?
don't. I'll eat. You give me beans, I'll eat them. But,
Okay.
but yeah, so this is really interesting. Just look at this. This 6-inch sub has become an 18-inch sub.
I'll tell you why it's not a 6-inch sub. Because a 6-inch sub comes cut, right? So you'd have a flat surface on this. This is a 12-inch. Because it's got 2 rounded ends.
I'm not sure I get what you're saying.
Well, they don't make a 6-inch piece of bread and then cut it and make a 6-inch sub. They take a 12-inch piece of bread, cut it in
yeah,
half.
you could. There's been some.
Well, you
places-
could.
Yeah, I've seen some places where they make 6. Haven't you seen like mini baguettes? That's like 6 inches. You could do
Yeah, but I don't think they do. I mean, it's been a while since I've had a sub, but I don't think they do that
that. What's this then?
at most places. This is now an 18-inch sub.
That's a big sub.
XL.
But this is what's
Make that a combo, $35.
for an 18-inch sub. That's pretty good. Well, no, that's very
No.
expensive. Canadian, oh, by the way.
Yeah, maybe.
If it was US, we'd just be broke. But look at this. We hit. I like to remind you, we were able to get out of the black hole's gravity, speed-wise. But look what's going on here. Like Jupiter is being torn apart. It's still getting pulled back in. Even
Well, it's over, right? It's all over.
Oh, Jupiter's
If
gone.
you're getting pulled, then it's done.
It's just being like stretched. It's like taking a rubber band and it just keeps going. And keeps
Well, there's got to be something too there where if you are being like if half of your mass is being extracted, is the forward motion part of Jupiter still able to progress?
Oh, it's a good question because you are correct. It's not. See how it's slowly getting. Look at that. See, its half is getting pulled back in.
It's our favorite part, the spaghettification.
We thought we got out. Just when you think you leave the black hole, they pull you back in.
So you've got your 18-inch sub.
Yep.
Your pinto beans and Romano beans. And your spaghetti.
Yeah. All for the price of $39.99. Black hole.
Okay.
But yeah, look at that. Even at 11% of the speed of light, Jupiter is not able to escape. So a race of Jupiter versus black hole?
Not going to happen. So your best bet is, as I'm saying, is that maybe you're more than 2 or 3 suns away. Maybe you have to start running at 10 suns away.
Yeah.
A distance of 100 suns away.
Yeah.
Then you would be able to escape the pull of... But as we know, there's no way Jupiter has any means of propulsion. Jupiter's not going anywhere. It's presumably sitting in an orbit as long as the sun is still alive.
Yep, and if that sun's gone, then Jupiter is...
But even if the sun is alive, the black hole has more gravitational pull than the sun. So now the black hole becomes the center of the solar system.
It's interesting you say that because that's our next black hole collision.
Okay.
Black hole versus the sun.
Okay, so let's take a closer look.
At what's going on here?
Yeah.
Yeah, I am more than down. So I think we're going to see some really interesting stuff. Obviously, we've already seen what's going on with the sun, but I think we should kind of break down what's going on step by step.
Let's do the timeline on this and break it down a little bit more.
Let's do it.
On this. I see you have a little timeline thing at the bottom.
Yes.
Currently there, we're 59 seconds in. 59 seconds in, and we're already, the sun is already egg-shaped.
Oh yeah, this is more than egg-shaped. This is like a paintbrush almost.
So the black hole's gravity has overtaken the sun.
Oh, just exponentially. Remember, this is 118,000 times the mass of the sun. So,
and because the sun is made of gas, it's now just becoming a stream of gas as we turn around in 2.5 minutes.
Exactly.
This is 2.5 minutes, and looks like the sun is now a stream of gas joining the accretion flow.
Yes. Again,
and there's the bending of space-time, as you can see. Boom.
Yeah, it's pretty cool. It's
like a little roller coaster.
Now remember, the accretion disks would be there for regular black holes, but for here we haven't put an accretion disk, but it would join rather than becoming its own. So we're seeing instead the sun become this black hole's very first accretion disk.
Very first. So this is a brand new black hole.
Brand new black hole,
Just
brand
formed.
New accretion disk.
Okay.
Congratulations, Mr. Black
I like
hole.
it. And what's going to happen too, we noticed in the last one, is it shot out as it goes around the accretion disk. It's going to shoot out, there we go, it's shooting out jet streams of gases.
Mm-hmm. And this is full of things like, I believe, like plasma and radiation.
Yeah, radiation. Those are radiation, but it's also somehow rejoining.
Because that, again,
because the gravity
is so much. So even if it wanted to, and the sun, at this point, the sun is no more.
Right, you don't think the sun could reform itself into something?
No, this is permanently an attraction at the black hole exhibit of space, and I think it's gonna do this for a while. Isn't that right, Peter?
Well, it's not just going to be like here on Space Sim. It's probably going to take seconds or minutes, but eventually this is going to actually take months or years of circling the black hole before all this hydrogen and helium explosive. What did we call it before? We called it thermonuclear energy release. It's going to be months to years before that's all absorbed by the black hole.
Which is why we see those accretion disks all over the galaxy.
Yeah, they're just waiting to be swallowed.
Yeah.
We're doing black hole, still the primordial black hole, all right?
Yes.
Are we ever moving away from primordial? I won't spoil it yet. Don't even tell me. Coming up later, maybe not primordial black hole, maybe some other black hole, but we won't tell you.
I won't tell you.
Okay, so this time it's primordial black hole versus sun.
Our sun,
Yes.
not just any sun.
Right.
Our
Well,
specific
did you
sun.
know that there is actually only one sun? The rest of them are all called stars.
It's crazy. Peter.
Sun is a name, just like Earth, Mars,
Jupiter.
Kepler 42b.
I guess that makes sense. Okay, fine. Well,
Yeah.
yeah.
Our sun.
Our beautiful
I don't mind
sun.
calling it our sun.
This is our sun, and as you can see, this primordial black hole, again, we've increased the size because, of course, the sun is bigger than Jupiter. If we were to put the sun, this is Jupiter. You remember how big it is? Look at that. Look at that size difference. Now, if you remember when we had it last time, Jupiter versus the black hole was a lot closer in size. Now, look at that. Jupiter's tiny, piddly even, compared to this black hole. So, you know, we're gonna have it orbit. We're gonna see some really cool stuff, and we can start explaining stuff like accretion disks.
Okay, well, now you just mentioned how we've changed the size of our primordial black hole.
Yes.
And if I look this up, so the primordial black holes are the smallest of the black holes.
Yes.
Scientists estimate that they were formed, within seconds of the creation of the universe, and they can range in size from 1/100,000th the size of a paperclip to 100,000 times the size of the sun. So there's a large range there, but also very small. They can be very, very tiny.
Yeah, and that's kind of
As opposed to the supermassive black hole and the stellar mass black hole,
Which
and
is
the
what we're
intermediate
used to.
mass black hole. Yeah.
Yes.
These ones can be very, very small,
Yeah.
or can also be pretty large.
which is perfect for
Yeah.
this simulation. Now, you can see here on the physical parameters, this thing, the mass is around 117,000 suns. So take the mass of
Right.
the sun, times it by about 118,000, and that is the mass of this primordial black hole.
So it's exerting the force of 118,000 suns
Yep.
upon one sun.
Upon one sun.
I don't like its chances, the sun.
Yeah, I don't think it's going to do too well. So let's just jump right in and see kind of what happens
Oh, there
here.
goes the egg shape.
Yep.
And we're crossing the event horizon, and we are now into accretion flow.
Yeah.
Joining the accretion disk, you see how we're bending space-time there.
Well, this is really interesting because this is where we really start to see the accretion disk really start to form as compared to other planets like Earth and Jupiter.
Why? Because this is fire. This is sun.
Yes, it's bigger, it has more gases, and these gases are going to react more. And we also have, I think the biggest thing, if I'm being completely honest, is that
I wish you would be completely honest with me in this show.
always honest with you, Peter.
Yes, thank
Those
you.
glasses look great. Don't listen to the comments. This has more, we have more evidence of actually what's going on here because we've seen
this happen.
We've seen this stuff happen before.
Not with the sun, but with other stars.
With other stars. So we actually have more of an idea of kind of what's going on here over this time. And what's really interesting is we can really start to explain kind of what an accretion disk is here.
I like it better when you go in reverse.
Oh, like kind of.
Yeah, it's like we just created a sun.
Yeah, just how did the sun make? Zoom. There you go. Easy.
It's not how suns were created, but that's how we just did it.
That's how we created
Yeah.
our sun. So this is really interesting. So I
I think what you were referring to is the luminous flare. Is that?
yes.
That's called luminous flare right there.
Yes, this is, and I think that's super cool because when on first glance, I think it's very easy to be like, okay, it's a black hole, it's affecting another celestial object. What happens to it? It spins around, right? It just kind of, it does the same thing as Earth. But I think we're missing a lot of cool, interesting details by simplifying it like that. One of them, this luminous flare, you can see here. Do you see that slight color change? See how it's kind of like an orange bright, and then when it gets to here.
So it's white hot toward the black hole and a
Yeah.
little bit more of an orangey color.
Yes. So this is that big change here.
So as it's going, hold on, stop there.
Yeah.
So one thing that can happen with these, and you had mentioned the color change as well, but one thing that's happening too is that the sun is getting a little bit flattened.
Yeah.
There's something called a pancaking effect.
Great name.
And following the pancaking effect, I'm going to guess it's called the unpancaking effect.
Yeah.
And the pancaking is a compression of the sun. So it's been all these gases, hydrogen and helium, being compressed, and then at some point there's a release, and it goes like that. You can see it. That's what's causing the luminous flare. It's explosive thermonuclear energy release, and the sun is flaring. And I think if you keep it going, that this big chunk is going to escape, is it?
Yeah,
Yeah,
right
look at that.
there.
But the gravity of the BH, the black hole,
Call it BH in the industry.
yeah, we call it BH, and it just gets sucked right back in.
Can't escape
Yeah.
because the black hole is 117,000 times.
Yeah, it was fun to see the sun stretched and ripped apart.
Mm-hmm.
So then everything's exploded. Oh, you're giving me. I know what we're doing here. We're gonna see if this sun can escape. the black
Usain
hole.
Bolt. So let's start increasing it. Right now we're at 11,000 kilometers per second.
And we're 10 suns away.
We're about 10 suns away
Okay.
from this guy. So 10 of these can fit in there. We're increasing it 17,000. Yeah, so let's start increasing and see how much it really takes to pull away. Keep in mind, this is obviously a farther distance than Jupiter or Earth was. But as we're increasing it, look at this. We're
That's
at
1/10 of the speed of light.
and it's still getting bungee corded back in. We're at 13,
Right. Okay.
14, 15, 16%. 16 around, let's even get the point. No, it's still slingshotting back. Around 16%, but you can kind of see, do you see that there?
What if we got it all the way up? I mean, the sun is light.
You just
Should we
want
get it up to the speed of light? Would it? Oh, there we go. So he's escaping now.
Yeah, let's see. What if do you want to move it a little closer and see what would happen, but it's still the speed of light?
Sure.
All right, let's try that. Let's see what would happen.
It's getting away.
Yeah.
Haha. It's getting away.
But the thing is, the sun, we think of it as light, but obviously the sun isn't light. It just
No, it's
emits
burning
lights.
gases. Well, it's
Yeah.
not burning. It's like thermonuclear reactions.
So it's just pushing out light. It's not light itself. So if the sun was light itself, it's doing just fine.
Right.
Unfortunately, it is not. So we're gonna push it back a little bit to where it was before, and we're gonna drop it to around.
Okay, now it's gonna. Oh, there we go. It's gonna slingshot.
It's still slingshotting. Let's try 16. Let's see what happens when we do about 16% the speed of light. And we'll start to see that pull. Again, this is just like Jupiter. This is just like Earth.
It's getting squeezed.
It's getting squeezed. It's getting pushed. Look at that. And this is an egg. We talked about eggs before. This is an egg.
It's total egg.
This is a glowing egg. If I had this in my house, I think people would be quite impressed that I had an LED egg like that.
It's enormous too, so it'll probably burn up your house.
It would, but it looked cool,
Yeah.
even for a split.
So at this
second.
point, it's being stretched. In order to escape now, it would probably have to increase itself to the speed of light.
Yes.
And even if in that case, it's already being pulled, so it would probably leave a remnant of it behind, and that would be swallowed up into the black hole or pulled into the accretion disk to circle for tens of thousands of years.
So it would never be the same. Our sun would be.
No, I mean, it's already
changed.
never the same. It's heading in another direction without us, so
Yeah.
most likely we're freezing to death in about 6 minutes, is it?
Yes.
8 minutes, I think it's
Check
8.
out that What If episode.
Yeah. What if there was no sun?
Uh,
There's a what if episode for everything that we do here. Just I'm not going to remember to bring up the title of which what if we're sending you to next, because we're not really sending you to what if. This is not the purpose of this. The purpose of this is for me and Stu to talk about cool looking stuff being swallowed by black holes.
like this beautiful sun. Look at that, just getting stretched.
Yeah.
Now that's a 12-inch right there. That's a
Well,
12-inch sub.
I think it's going to turn into a lightsaber
Ooh.
in a bit.
Look at that. It's a lot faster than it's Jupiter, so it's just that spaghettification is really starting to hit there. And what's also interesting is you can see that light. It's so much brighter. If we were to kind of back up a bit, like, it's that orange. It's kind of, this is what sun we're used to, but then...
The more activity, the hotter it gets, and the whiter it
Exactly.
gets, right?
Yeah, and we're kind of seeing that pancake effect that you were talking about earlier as well.
So stand by for what we call explosive thermonuclear energy release.
Yeah, as it slowly gets away. I think the best way to say it is that Nothing escapes a black hole.
No. I mean, we could
have to
stop
be-
right there and say nothing escapes a black hole, but it wouldn't be that exciting because we want to focus on the next one.
The next big sun.
Okay, this time, wait, we're looking at the sun again.
This isn't the sun, although it certainly looks like it. Let me plop the sun beside. This is UY Scuti, and this
We say UY Scuti.
Do you?
Yeah,
You're a Scuti guy?
I say UI Scuti.
I like Scuti, but
Okay, well, we're going to have a difference of opinion for the rest of this segment.
yeah, it's just fully canceled over Scuti. This is,
That's the wee sun right there?
yeah, we can't even see it. That's
Oh
how
my
tiny.
gosh.
Look at that. And then if we were to look, whoa, this is.
Well, I
what-
like UI Scuti's chances.
It feels pretty good, but then if we look at the black hole,
That's pretty big too.
it's a pretty big black hole because we're also, again, this is us matching that size. So, you know how last time it was about 117 times the mass of the sun for our black hole?
Our black hole was 117. Oh, so you're increasing the size.
117,000 times the mass of the black hole.
Right. You're increasing the primordial black hole so that it's similar to...
To what we're doing it again.
that
So
ratio?
this time it is 2 times 10 to the power of 8 mass of our sun. That
Okay.
is, I think, around 220. I want to say 20 million, if not 200 million. Someone can do the math. On
Please
that
at home,
one.
please answer in the comments. How many...
How big is that?
What? Yeah. What? I didn't understand that number.
Let us know.
So UI Scuti is a star that was once thought to be the biggest star in the universe, until we got more telescopes and we found out that there's some bigger stars out there.
Mm-hmm.
But it's about 1,700 times the size of our sun.
That is massive. I mean, we can really see it here, where it's just like.
Where you put them side by each.
I mean, yeah, side by each. You can't even see the sun.
No.
The only way we can see the sun is because of the fact that it says sun.
It almost feels bigger than 1,700 times the size.
It feels like it just never ending. But think about that. That's our sun. And you saw the difference between the sun and Jupiter. You saw the difference between Jupiter and Earth.
Yeah.
And we are just tiny little details on Earth. This is how big, how massive
So now this
is.
one's fighting a bigger black hole. So
Yes.
it's not necessarily the. That means it's probably going to be the exact same thing, isn't it? If we had a smaller black hole and a smaller sun, and then we just made a bigger black hole and a bigger sun, aren't they just going to be doing the exact same thing? It's not like we had the small black hole and a big sun.
Yep.
That would be a difference.
Well, you would be correct, but actually, this is where physics starts to really come in, and we talk about
not
things.
Good at physics.
This is where we talk about things like tidal forces.
Okay.
So one of the things is that as we increase radius, tidal forces make it easier to disrupt the core. Is the best way to describe it.
Right.
So as we make it bigger, it's easier to pull apart. Is the best way to describe it.
Even if it's completely solid.
Even if it's completely solid.
Now the sun is not solid, but so a smaller sun is harder to pull apart than a bigger sun.
If the
Bigger star.
Yes, if the density, most of the time as we increase it, that density increases as well. This UI Scuti is 1,700 times the size of the sun. That's what you said.
Okay, yeah,
But
I
right
did
here,
say
the
that.
mass, it's only 9 times the mass of the sun. That's not that proportional, right?
But it's still the same density?
It's a different density because it's only 9 times the mass of a sun.
Okay.
So you would think it would be like at least 1,000 times more dense than the sun, but it's not. It's actually, if we were to shrink UI Scuti to the size of the sun, it would be much, much less dense. And because of that, even though we've increased this radius huge, the density hasn't increased with it, which means that this black hole is gonna have a really easy time
It's just it'll be just like
just popping open.
a cotton ball.
Exactly. Yeah,
Okay.
that's a great way to describe it.
Okay, so let's see what happens.
Let's start that simulation.
And so this is taking longer. If I'm looking at your timeline down there.
Yes, the bigger it is. Also, look at that. Isn't that cool? That's that jet stream. We'll talk about more of that in a sec. And that the radiation, all these explosions, happening.
Wow, this is a lot.
It's a lot cooler than our own sun. But that's because it's bigger. It's got more to work with, you know? It's gorgeous. We're having a hard time.
Something's getting away. Don't let it get away.
That's a real question. Can the black hole grab it?
It has to. It's probably the same as you were saying with the slingshot effect.
As it slowly gets pulled back in.
I don't know. It's not looking like it's make it go faster.
This is about as fast as we can go.
Okay, never mind. Don't make it roll.
But look at this time, by the way. It's been 33 days. But I think that's what's so interesting. This is great to pause. There's a lot of things that we can really talk about. I think a big thing to kind of note is that one is that time difference. Look at that. It's been a day.
How long it takes.
Day, and at this point, this had been a couple of minutes for a sun. This had been several seconds for Jupiter. And at this point, this had probably been like 0.2 of a second for Earth. So it's interesting. It's easier to tidally disrupt, but it takes longer to pull it apart.
It's easier, but it takes longer.
Yeah.
You'd think it'd be fast.
You think it'd be fast, but with these giant objects, they're just that big.
They are that big. So so the same sort of thing happens as happened to the regular sized sun.
Yep.
There's no way of escaping this.
Nope.
It just turns into the accretion disk. But it's fun to see the big bulbous explosion at the head of the snake.
Yeah. I think what's really cool about here is that this is a great example of what we were talking about with the sun, of what this accretion disk is kind of doing, right? This is gases, dust, debris, because keep in mind, this is a new black hole, but if it was part of another black hole, it would also interact with what else was going on in that accretion disk. So it would be interacting with all these different elements and at insane speeds, pushing out a lot of energy, and it would create stuff like this, right? Where it bottles together and shoots stuff out, and that's that jet stream effect that we were talking about earlier as well.
So this is another extremely large accretion disk that can probably spin there for years and years and years.
Years and years and years.
And is also losing mass at the same time.
Well, what's so interesting, think about that. There's so much power being shot out from this accretion disk that it's able to actually have some of it escape a black hole. Because that's how much explosion and jet streams and shots are going out here.
That's power.
That is power.
It's like
in the palm of your hand.
It's like an F-150.
Yeah, but for space.
Yeah.
Yeah.
Okay.
Which is really cool. So maybe we can break down a little bit.
Break it down in timeline form?
Yeah, let's do it. So we've got it set up here for our race.
The race to escape.
The race to escape.
Which we know is not really a possibility. No. I mean, it is, I suppose, if you could move
speed of
light.
Yeah.
And there is light in UI Scuti, but it's not made of light.
Nope.
It just has light.
And
it's not very light. It's very heavy.
Relatively, it's pretty light, actually. Only 9 suns is pretty...
Can you lift it? It's not light.
You don't need to ask that, Peter. You know the answer. Of course. Let's start...
100 astronomical units away.
Yes.
That's 100 distances from Earth to Sun that this UI Scuti is from the primordial BH black hole.
So it's pretty far. So we're going to start increasing it, and we're starting to see it earlier and earlier.
That's 1/10 the speed of light.
Yep.
And it's still doing...
It's still slingshotting around 12, 14, and then around here, even then, look at that slingshot. See that feature starting to come in there?
And sorry, where are we? That's 15?
15% of the speed of light. That's like, I don't know. I can't do the math.
An eighth?
Yeah.
No, it's not.
Is
right.
that 16?
Sixth.
So let's try it around here. This is 16% the speed of light, and it should start to have a little of effect. So there's no way that this sun was able to travel this fast.
No.
Obviously. But being able to...
There's our squeeze.
This is the big explosion.
We're getting egg-shaped here.
There's that egg shape kind of pulling in there. It is kind of interesting how distance-wise, we're so much farther away, and we're going so fast, and yet the same things keep happening over and over because a black hole is that powerful gravity-wise.
Are we seeing this at home?
Yeah.
What is this wall clock time? 0.72 minutes, but down here I'm seeing 10 days.
Well, this is in time. That could be actual time. That could be us. See, like an actual
0.9 of a minute.
So it's been about 1 minute of our time that we're watching this, and it's been a week time. It takes about a week. Again, look at that difference in time. You know, it's a lot slower of an object, so it takes a lot longer to stretch out and build. But again, I think the same thing's going to happen that happened to our big, beautiful sun.
Yeah. Yeah, everything's,
Hitting the same thing?
Hitting the same thing. It's all the same. It's all the same.
It's all, life is basically the same.
Life's all the same. Okay, we've got our primordial black hole, and this time it's not just going in taking one celestial body. It's got its sights set on 8 plus 1, 9 celestial bodies here.
Plus an asteroid
Plus
field.
oh my god, we got lots of celestial bodies.
So many celestial bodies here, and yet none of them are surviving.
And our primordial black hole is back to the size of...
It's about slightly smaller than Jupiter, so around the same size as when we did our Jupiter simulation.
Okay.
So
let's say... Oh, and I see you've got Pluto there.
Yeah.
So it's starting with everyone feels bad for Pluto.
I felt bad for Pluto.
Sure.
I grew up knowing Pluto as the 9th planet. I feel bad, you know?
Well...
Do you think kids today feel bad about Pluto?
I don't think they care.
They don't care at all?
No, I don't think... I think they hear about it and they think they're going to Disney World.
Do you care about Pluto?
I do care about Pluto, but I'm also worried about Planet X out here. I'm assuming the primordial black hole has already swallowed up Planet X.
Planet X is gone at this point. Yeah.
Sure. Okay, so now it's bearing down on our solar system. And if you zoom out a little bit, lucky enough, it's entered our solar system. And give me the overhead shot again.
Yeah.
Or no, right there, yeah. So it's actually entered our solar system at the exact time that every single planet is lined up in a straight line.
Yeah, there's a name for that. I don't know what it's called.
Impossibility, I think it's called. Is it?
It happens once every
billion years?
Something like that.
Okay.
Yeah, I'm sure it's about
Okay, so first off, I mean, by the time it gets to this point in space, it's not just bearing down on Pluto.
Yeah.
It's probably also exerting some force on everybody.
Everything, because we saw that from the races, right? Even if we put them
far
several
away.
distances, several sun distances away, that black hole comes for us all, right?
Yeah.
So yeah, every single thing is going to instantly feel. Before we even hit play, I think it's important to note that if this was just a pop into existence, every single thing would feel that pull instantly.
So my guess is nobody's really got a chance of getting away here, but let's see how it plays out.
All right, let's start this simulation as we go up.
It's interesting. Note when we say that, how much gravitational effect or with all the tidal force that this black hole is exerting, even if it just appeared there for half a second, it would probably pull
just planets apart.
Planets apart. Yeah, we don't 100%. Need to see it. We will see it because it's going to be great. But we don't need to see it suck up every single planet to know that it's going to have an effect on our solar system.
Yeah, because that's just how fragile everything is. So here's Pluto. This is Uranus.
Amazing to think the solar system is fragile. The size of the solar system, and it's fragile.
Actually,
I mean, when competing with a mass like the black hole.
Oh, 100%.
Yeah.
You know, it's a good little reflection. You know, we're
we're not as safe as we think we are.
Nope. So live life to your fullest, guys.
Live it to the fullest. Go skydiving.
Yeah.
Because what do you got to lose?
Be safe about it, please. Let's not. Okay, so we're gonna hit play. It's been like 0.000 seconds. Even before that, Pluto has been, because of how close it was, it's been sucked in even closer, even faster than that. So Pluto is gone. Neptune's already here.
In 0.000 seconds.
Even less than 1,000th of a second, Pluto is gone. Because in the setup, Pluto is pretty dang close.
Right.
So it was less than a sun away. So it's about 300 Earths away. But this is a big black hole. So Pluto, small little dwarf planet, gone in an instant. We can see it here actually. So we'll see maybe if it can survive or anything. Odds are it's probably not going to. So as we slowly, there's Pluto there. You see how it's starting to burn up.
Okay.
And then sucked into there. I'm gonna let the simulation play all the way through and then we can kind of break it down. So I'm gonna hit play. as it continues, there's
Oh,
Uranus,
just sucking.
everything. There's Saturn,
Next,
gone.
Jupiter.
Jupiter gone. As it slowly gets into. Look at that, Jupiter. We've seen Jupiter
Wow.
gone in an instant.
Then this is the asteroid field.
Yeah, all these beautiful asteroids. Amazing time. There's Mars getting in there too. And what's interesting is that the sun is also being sucked in there. Look at that pull. So all these asteroids are getting sucked in there. They can't do anything about it at this point. Mars is freaking out. There we are.
We're far enough to start trying to get away.
Yeah, because we're about like several radius of the suns away. So we're like, you can really see, we're starting to really feel that like tidal. It's a little bit smaller because there's a lot of things, but we're gonna start to feel that pull. It's already starting to morph and freak out a bit. As next up, Mars lines up before we have to face our inevitable
Death?
doom, our inevitable death.
Okay.
We probably see it in the sky. I mean, we can see
Oh,
Mars
we're watching
from our
it?
sky.
Well, we
right?
probably wouldn't be watching it because probably things are already happening to us.
Yep.
And we're already feeling the effects of the tidal pull.
100%. We would feel full pull from everything.
We've got tsunamis and earthquakes and volcanoes, and we're not really interested in sitting on a hill and watching Mars get
and there's
sucked
Earth in an instant.
up. It's quick.
So,
And this is all happening within a minute and 20 seconds.
Yep.
And then the final.
And because it's smaller, it's going to start creating that accretion disk. And because there's a little bit of velocity to this black hole.
This is a
look at
cool
that.
angle. We haven't seen this angle before.
Yeah, look at it being shot out.
So this part back here is.
This part leading, that's our black hole. See how it's sucking everything in there?
Oh, I see. We turned it around.
Yeah, we just kind of like saw it from the backside, but see, it's sucking everything in there. Again, this is simulation, so it would start to create that accretion.
The accretion disk, yeah.
But let's just pause there. 8
Okay.
minutes, guys.
Yeah.
You've been watching this live stream for longer than 8 minutes, and in that time frame,
Well, we've seen a lot of things die,
and now we're seeing a solar system.
just disappear.
Just
And
disappear.
swallow up the solar system in 8 minutes.
Yeah. So we can kind of break it down, and we kind of explain what's missing.
I kind of hope we go that fast.
You think so?
I mean, I'll be dead long before the 8 minutes is even
Yeah.
half. I'll probably be dead within 3 minutes.
Is there a way you would like to go, Peter?
I would like to be sucked off the surface of the planet and flying through
Space?
space. Yeah, sounds like fun.
That'd be kind of fun.
Yeah,
Last little hurrah before.
yeah, and then I mean, I'd be. Unfortunately, you wouldn't be able to breathe in space, so you'd be dead within seconds. But
That's fine. It's better than being spaghettified. Although you'd be spaghettified anyway.
eventually, you get spaghettified, but you're dead.
Yeah. So let's talk about this. This is the black hole, and as we go through, I think a big thing to note about this simulation is that it's pulling things in one by one, right? Saturn is being pulled in, Uranus is being pulled in, Neptune is being pulled in. But what's kind of important to note is that we were talking about was that the solar system is fragile, like what you were mentioning earlier.
Yeah.
And so it wouldn't be this, like you talked about that line, it wouldn't be this linear.
Right.
So many things could happen, you know? The sun's being pulled. The different things would be pulled. If you have a smaller density, you might be being pulled a little bit quicker than the...
Well, face it. Once this black hole has moved the sun,
yeah.
even if the black hole disappeared seconds later, it's messed up our solar system for the rest of eternity.
Mm-hmm.
In fact, Earth is probably flying out of orbit into some odd
Different part of the Milky Way.
part of the Milky Way. Yeah.
And that means no survival whatsoever.
Yeah, that's just how disruptive these black holes are. These nasty, pesky black holes.
We've just been seeing too many of them taking over
Yeah.
the galaxy. So yeah, as we back up, as it slowly starts, this is where, I think a lot of people think that we're protected from like this asteroid belt. But say, for example, there's a lot of little things that you kind of have to realize. Say Jupiter was to be swallowed by this black hole and then suddenly disappear. Well, Jupiter is also super important for our solar system as well. Jupiter is part of our solar system. Its large gravitational pull has pulled away asteroids and comets.
Sure, yeah.
And stuff.
I mean, we're not going to be worrying about that at this point because we're all
No.
going to die in within minutes. But yeah, Jupiter has always been a great help to Earth by absorbing or deflecting asteroids or comets and things that are headed our way to create extinction type events.
Yeah. And here we're
And
seeing
then that would be our protection gone. But
gone.
it doesn't matter, our protection is gone because within a minute or so, we're going to get sucked into
We're gone.
a primordial black hole.
And this is where that, and then the sun, it just kind of like what were you talking about earlier, where it would, even if something this small, much smaller than the sun, were to just kind of go through it, completely disrupts it. That core is gone. And this is we've now completely changed the essence of what the sun is. Right? It's no longer, the core is gone. It's being sucked into the black hole. It would start to create an accretion disk.
It's really weird that something that small can overpower the sun.
The sun. Something smaller than Jupiter is able to take over the sun, but that just shows you the power, the absolute power of the black hole. And it kind of makes me wonder,
Can we get away?
can we get away?
I don't think so.
No.
All
I don't
signs
think
point
so.
to no.
And instead of doing a race, we're going to do something a little bit different. 'cause
Oh, okay.
We've seen it. We're going to do... This one I thought would be fun. This is just all the planets close together, orbiting, and creating a nice little accretion disk for our primordial black hole. And we're going to see what happens here. I'm going to bump up the...
What is this?
This is just all of them. As you can kind of see, they're just kind of all together. We're all
Yeah.
kind of close together. We put a black hole in the middle.
And we haven't been swallowed?
And we're about to see what happens as they all create an accretion disk around us. It's just going to look really pretty.
Okay, so currently they're still in their normal orbit.
Yes.
Although where's the sun?
There is no sun here. Sun has already been swallowed up. This is just like a fun little hypothetical if all the planets were just kind of around.
Okay, so
One
if the
black
black
hole.
hole took the place of the sun.
Exactly. What would happen?
Okay.
And turns out,
Well, let's do this. You've got a little experiment here. So if the black hole replaces the sun in the center of our solar system, what then happens with the planets that are orbiting where the sun used to be?
yeah, we're noticing things like this is Mercury. Look at that. Burning
Looks
up.
like it's in retrograde.
Don't sign any contracts. That's what I learned.
Don't sign a contract when Mercury's in retrograde.
And look at that. Mars is burning up. Earth is burning up.
Yeah.
Venus. Look at all these planets, these smaller planets just like being destroyed within, again, hasn't even been a second here.
0.69 seconds.
Yeah.
Neptune is melting.
Neptune and Uranus,
The gas giants
are both melting and
wavering.
being pulled in. And
Okay. So I'm going to assume that these, they're orbiting. They're not orbiting as fast as they're going to be in a few seconds when they all become part of the accretion disk.
part of the accretion disk, you're correct. And I think it's a good thing to kind of talk about. We talked about how size kind of has that time difference. Like, look at that. Mercury is basically already this husk. It's already turned into what we saw with Earth. Earth is still taking a little bit longer to get there. Jupiter hasn't even really, like, talking about time.
Get dizzy here.
Sorry about that. Jupiter hasn't really been, it's starting to turn into an egg, but it hasn't really been affected too much.
Right.
It's just getting a little bit of that
Yeah,
pull.
I can
It's not,
see it there.
it's
Yeah,
not
well,
turning
it's
into these.
moving now.
And that's just showing you that size really dictate, like time really dictates.
Size matters.
Size matters, as we see this slowly go around here. Because again, it's only been 2 seconds. Earth, gone.
Gone.
Mercury, gone. Mars, gone. So it wouldn't be a very fruitful
So,
solar system.
no, it really wouldn't.
No.
So it would be a dead solar system.
Yes.
There would be, I mean, at this point, it's not a solar system because we've already swallowed the solar,
It'd be a black
the
hole.
sun.
It'd be
Yeah, it's a black hole system,
Yeah, BH system.
which, as we know, will only last 2 seconds.
Yeah, at least for us.
Okay.
Yeah, we could let this play out. It's gonna
Yeah,
take.
play it out. Oh, how long does it take?
It's gonna take a little while before
Okay,
we.
run it in fast motion.
This is as fast as we can go.
You can't do it.
Unfortunately, we gotta.
Technical limitations, people.
We
Well,
have
why
a
not?
Slower. We have a slower.
Oh, that's kind of cool. Whatever the heck's going on there.
That's just that change. That space-time change.
It's our Dyson sphere. So we've seen a black hole take on Earth. We've seen the black hole take on the sun. We've seen the black hole take on a bigger star, the entire solar system. Now, what about an entire galaxy, Stu? Do you think we could make it as big as a galaxy? There wouldn't be a black hole as big as a galaxy, and it couldn't swallow an entire galaxy.
Well, let's figure that out.
Let's find that out.
Let's just
okay.
show you a quick little size difference. This is our sun, and this is Sagittarius A, a black hole. So this is a big boy. This is a big black hole.
So Sagittarius A is a black hole that already exists in the center of our galaxy, the Milky Way. It is Sagittarius A star, and it's the thing that's centering our Milky Way.
Mm-hmm. So let's kind of see. Let's just see how big this Milky Way is, because maybe a black hole can take it down. So I'm gonna click this disk galaxy. I'm gonna click it.
Disk galaxy.
We start to realize, Peter, where is that dang old black hole?
Sagittarius A star or our primordial friend?
Our primordial, well, the one that we just put down was Sagittarius A, and as we can kind of see, it's nowhere to be found. Sagittarius A is right in the middle there. Here it is. This is our Milky Way. Gorgeous, nice little galaxy,
Yeah.
beautiful so much. So let's see what how big Sagittarius A is, and that's where you start to realize the scope of how big a galaxy is. Peter, how big is the Milky Way galaxy?
It's about 100,000 light years across.
It's very big. That's
Yeah.
huge.
So
it would take light 100,000 years to travel from one end
to the other.
to the other.
Yeah, unless it got stopped by Sagittarius A star, the black hole in the middle of the Milky Way galaxy, then it would swallow that light, and it wouldn't make it all the way.
Mm-hmm.
So you kind of have to take a side streets.
I have to get a little bit around.
Yeah.
110,000 years, let's say.
It's so big that our solar system takes 240 million years to orbit the Milky Way.
Wow, that's very big. And as we start to go in there, look at this. This is 2.63254 E plus 09 AU, which is astronomical units, which is how long it takes from the Earth. It's massive, absolutely massive. We're still scrolling. It takes forever to get to. We are now finally seeing Sagittarius A after all this time. And again, if we zoom out, you can see just how big the Milky Way
My gosh.
is.
Okay,
So
so it's big.
how do black holes do against the Milky Way, a disk galaxy?
Well, it's I'm going to say it's probably not going to swallow the whole thing, but it is going to cause a trail of disruption as it goes through and swallows a few things here, there, and most everywhere. But there's a possibility it could swallow the whole Milky Way, but it would probably take 16 billion to the point E plus 09 years to do it all.
To finally go through it. That's true.
And at the same time, it's already fighting with another black hole right in the center of the Milky Way, Sagittarius A star. So
That's true. So, as beautiful and as powerful black holes are, they can't really. Again, I think we're safe.
I think we're
Well,
yeah,
If there was one nearby, it'd be bad. But where we are right now, I think we're
Fairly
perfectly-
safe.
We're fairly safe.
okay. So should we face off a black hole versus a black hole?
I love that idea. Let's do it.
Okay, so now we are on our final experiment of the show, and it is black hole versus black hole.
The final showdown.
The final showdown. This sounds like a Star Trek movie. So when two black holes get together, you would think, I want to attract you, you want to attract me, so they just come together like that. Why is...
Match made in heaven.
Yeah, match made in heaven. Why don't two black holes get married every day?
I guess it's just because they're not saying, oh, you like me, I like you, let's get together. It's more like, I like you, come over here. And the other one's saying, well, I like you, you come over here.
Okay, so they're standing their ground and saying, I'm the big
Yeah.
cheese in this neighborhood.
Yeah, think of them like holding one rope, and they're both pulling it.
It happened before two black holes came together, and was the first ever direct observance of gravitational waves ever that we've ever experienced. And it only happened 2015.
Wow, so just a little over 10 years ago.
Yeah.
Wow.
A little over 10 years ago
Really
was the first
recently.
time we've ever witnessed direct gravitational waves. What happened was two black holes about 1.3 billion light years away came together. Each of them very large. One was 36 solar masses. One of them was 29 solar masses. And they were fighting each other like we were talking about. And finally they came together, created a new black hole of 60 solar masses, and actually lost some weight in the process.
That's true, because they're not going to fully come together. They're going to shoot something out during that.
Right. So they shot out 3 solar masses worth of mass in gravitational waves, and that's how we were able to experience the gravitational wave.
Which is crazy to think that it's billion light years away, and
we can
detect it.
We didn't really feel it. Like, I didn't really get
The shimmers.
yeah, but we detected it.
Yes.
Yeah.
Which is absolutely amazing to see, and kind of terrifying.
Yeah.
That it can shoot that much out.
It's a ripple. So basically what that is a ripple in space-time. The gravitational wave is something that we can observe as a ripple in space-time.
And this is a great way to kind of break it down, because one thing I do want to note is that, Space Sim is all about efficiency. It would not take this quick. It would be much longer time for these two to fight it out.
Yeah, so millions and millions of years.
This is only seconds. It's saying seconds down here.
Yeah, we're showing it in seconds, but nothing actually moves that fast in space, does it?
No.
No.
And you can see we're kind of getting them closer and closer until,
Boom.
and that's where that ripple that you were talking about
Gets shot out.
gets shot
And now
out.
this can happen, doesn't matter if it's two primordial black holes or two supermassive black holes or two stellar mass black holes or two intermediate mass black holes. You can take your pick.
I agree. It doesn't matter the size of these black holes. They're going to. It's the same thing, just different scale.
Yeah, yeah.
And it's going to take a long time to get it done. But once it does get done, then we get this beautiful.
So it takes millions and millions of years, but then at one point they're just like, well, okay, let's get married.
Yeah, in just like a millisecond, they're like, you know what, this fighting's stupid. Why don't
You're
we?
dating and you're dating and you're dating, and people are asking you questions. Are you guys ever getting married? What's going to happen? Blah, blah, blah.
Maybe.
And finally you just say, forget about it. Too much pressure.
We got married last Sunday. Actually.
Bang.
Bam.
Yes.
And that's it. And then a new black hole is made, and that's history. Yeah, that's space.
Okay, so ladies and gentlemen, that's space. So thanks for joining us. Thanks for all the information, and thanks for taking us through the space sims and showing us what would happen if a black hole encountered Earth, Sun, large star, Jupiter we did as well.
Jupiter.
Yeah, we did the solar
Solar
system,
system.
Milky Way, and finally, black hole versus black hole.
And the winner is usually black hole.
Black hole. Black hole always wins.
Always wins.
Yeah, it's like the house in Vegas.
House always wins. Black hole.
Yeah.
Always wins.
Anyways, thanks for joining us. You got any more questions for us, or you want to see another one of our Space Sim marathons? Leave us some messages in the comments section, and we'll take them very seriously. And maybe you might even hear back from Stu, or me.
Or you. Or,
Right.
or both.
Thanks for joining us.
Today, we're simulating what would happen if a black hole came for Earth. But that's not all. We're also going to simulate black hole collisions with Jupiter, our sun, even the entire solar system. Let's get into it.
Hey everyone, welcome to another episode of Space Sim. It's What If Space Sim.
That is correct.
Today, I'm here along with Stu. Again,
Hello.
I'm Peter. And this is a project of What If, and we're going to take you through the Space Sim program where we simulate things in outer space. First of all, let's talk about black holes.
Yeah.
black holes are not what people think. They're not this big vacuum cleaner that goes all through the universe and just starts